Hopefully the sound's going through there. And when I messed up on that one before. So sulfur, 6 bonds, phosphorus, 5 bonds. 5-pointed stars, 6-pointed stars. So your phosphates and sulfates. This will make it real easy doing that. All right, now coming over here, here's another cartoon I like. This is the seagull. I call it the citric acid seagull. Carbon, seagull, get it? So carboxylic acid, carboxylic acid, carboxylic acid. Look at that, 3. You see this drawn, it looks really weird with all the seeds and stuff, but now drawn as a cartoon, I think it looks much easier. And nuclear chemistry, nuclear physics. Okay? Introducing quarks. How do quarks work? Quarks are what make the protons. Quarks are what make the neutrons. Even astronomers don't convey it good enough to kids, I don't think. The sun is actually making neutrons. And how it does it takes the proton. 2 up quarks and 1 down quark. After the Big Bang happened, spread out all these particles, the majority of them were protons. Stars, gravity took over when the sun and stars started fusing protons, hydrogen protons. These are just the nuclei. That's why you can't really call them hydrogens, because you need the electron to make it an atom to call it. This is just the bare nuclei. They're so high in energy inside stars that the electrons aren't held. So you're binding a proton to a proton. When you smash it together, you know what you get? You get an up becoming more massive to a down. So in order to balance that out, you need to make antimatter, which is in the form of an anti-electron, which is called a positron. So the positron is the first reaction in the sun. It's making antimatter. So what you end up with now is a neutron. More massive. I won't go into the mathematics of the charge. There's a +1 on the proton, nothing on the neutron. It's neutral. And it's new, so that worked. What holds the quarks together are these gluons. So there's 3 for that, 3 for the proton. You get a proton bound to a neutron when you push 2 of the protons together. This is called deuterium, a deuteron. Deuterium is when it's got the electrons, but just the bare nuclei here. This is the first building block to any other element. 2 protons won't stick together. Neutron by itself will decay on average in 12 minutes, I think. So, a proton bound to a neutron all of a sudden is more stable. This is what is happening in the sun right now. Everybody will say, oh, the sun makes helium. Well, in order to make helium, you have to make a neutron first, and then helium is 2 protons. So what will actually happen is you'll have to have 2 of these form. And that's the net reaction, but according to their theory is another proton will hit this, and then 2 of those will get together and kick 2 protons out, and what you end up with is an alpha particle. And the alpha particle is 2 neutrons, 2 protons. Can you see that in there? So that ends up with a net 2+ charge. That's the alpha particle. Well, I call it the alpha fishy. Okay? Alpha particles, you hear from alpha decay. Well, this is alpha building. So 2, just like 2 protons wouldn't stick together, 2 alpha particles won't stick together very long. So if you have 2 that stick together, before it splits up in a fraction of a second, if another one hits it, you will get carbon 12. This I love because you'll hear that carbon is the most life essential element. Well, it's carbon, nitrogen, and oxygen technically. But carbon is 3 alpha fishies. And this is what burns me with the astronomers, because they say red stars, oh, they're cold, they're not hot like blue stars. Well, in the core, they are. So you need a higher temperature. Our sun right now is only hot enough to fuse protons into neutrons and then essentially making helium. Later, if it follows the progression, it would form a giant red star after all the hydrogen's used and you're left with all the helium, alpha particles. More gravity would go in. You go from 10 to 15 million degrees to 100 million degrees. Then you can fuse 3 alpha fishies to make carbon-12. So this is a cute little drawing. You got 3 little fishies swimming in a sea. Get it? C for carbon. What's next? Carbon-12. Sail the 7 seas. Add 4 alpha fishies. What do you get? Oxygen-16. Notice how these elements are so well known. We breathe oxygen. We eat carbon. Next in the progression is the noble gas neon. Neon is 5 alpha fishies. Now what's cool about the alpha particle thing is alpha decay. I use it as alpha decay is like a alpha fishy jumping out of the nuclear bucket. This is the nucleus. All the alpha particles in there, well, if it's an alpha emitter, it's going to decay by emitting alpha particles. So it's like a fish jumping out of the bucket. Isn't that cute? Now this is what I would think. I think of the show The Jetsons in the 1960s. When little Elroy went to school, kindergarten, he would be studying nuclear physics, wouldn't he? This is what I think our kids should be doing. So now with the cartoon book, I think we can do that. And I think that's going to about do it for the tour of, no, tell you what. We're going to show you the DNA. This is the other thing here. DNA is something that seems to mystify the teachers so much, which is ridiculous. So now with the cartoon characters here, remember we had Ruby ribose? So here's Rhonda ribose. Color coding it, she's to cysteine. This is a 1-ring base, so that gets the longer names. See, everything's backwards in science. So you got purines and pyrimidines. If this is a smaller, because the other one has 2 rings, smaller, it gets a longer name. So pyrimidine is what cytosine is. These are all just words to you, but that's why you got the color coding. Yellow, C, only goes with Rhonda. Now what's Rhonda going to do? Rhonda is going to form a 3 hydrogen bonds to guanosine. Guanine. Guanosine, depends what's on the side here. See here, the 2 ends are aliens. Here are the aliens on the G. So these provide the protons on G. Here are the protons from the N on the cytosine. That's why C and G bond together. C won't bond with A because A will only do 2 bonds. See up here, Ricky ribose. Ricky is for T, or this is he shouldn't have that because it's a DNA. See here, RNA, what? T for DNA is uracil for RNA. So we have this drawn different later, but you see this only has 2 bonds. It's got the nitrogen, and this is what I started finding when you drew the cartoons. The nitrogens were always in the middle. See, nitrogen, nitrogen. Nitrogen here, when you get the adenine, which was down there with Ruby. Ruby and Ricky are the only 2 that go together. Rhonda and Randy ribose. Randy's the green, so yellow and green, blue and red. So it's a color coding thing. And then what you find is what holds these together are the phosphates. So see here, the phosphate star, 5 members star. This is a double bonded O. This is a single bonded oxygen out there. Negative charge on it. What's that? that was the equivalent, if you remember. I call it the three-headed monster. Where was the three-headed monster? Over here he is. Get that in the center there. Here it is. So see, when you get the phosphates here, you got O bound to a P, O bound to a P, and then another one. Double bound O gets 2 electron pairs out there. But this one, having the negative charge, means it's got the extra electron. You got 3 lone pairs on that oxygen. So I call that the three-headed monster. So we can get a close-up of that. It's a three-headed monster. And here's the adenine I was talking about. See, the N is in the middle. N with electron pair, N with a proton. So that does the double bond to, we're off camera here. So Ricky and Ruby. Ricky's base. Adenine bonding to that. That other end had the electron pair, remember, and the other end had the proton up there. So that's how that bonds together. Let's see, do we get everything on here? Again, we're running out of time. Our tape already ended, so we're running on DVD time here. Running on DVD time. So here's another fun little drawing was phenylalanine, just back where it was here. Phenylalanine looked like a little punching bag. See, whenever you get the benzene ring, there's like a little face in there. So phenylalanine, here's the nitrogen, carbon, oxygen, that's the amino acid backbone. There's the carbon with just a benzene ring on the end of it. That's amino acid phenylalanine. So we call it the phenylalanine punching bag. Doesn't it look like the clown, one of those balloon things that hangs up, or the old clown used to punch and fall to the ground and come back up? Well, here's one we didn't do, vitamin C. Vitamin C is also known as a scorbate. So we call that vitamin C. To me just looked like Zorro. OH, OH, carbons in there, OHs, OHs, OHs with the oxygen in the ring, double bound. You'll see vitamin C looks a lot like glucose, and you'll start seeing these different things by using the cartoons. But see, as Zorro, he says, "Back, you scurvy radicals." And he's actually got a college degree. He studied chemistry. He's got a college degree. And I think the stars are useful when you get into some real higher dimensional chemistry here. Showing the sulfur with the 6 bonds and phosphorus with the 5 bonds. When you introduce oxygen to this, you can get like 5 different, they're called oxyacid series. You get H2S, HSO, HSO2, HSO3, H2SO4. Phosphorus, see, even I'm getting confused. So I won't confuse you anymore. Here are some of just the little, I've got a little of the cartoons all laced in and out of here. So what would this be? You got a carbon double bound to an oxygen with 2 H's. So C is usually a methyl group with 1 oxygen. This would probably be your acetic acid, right? No, acetic is 2, so this would be formate. Formic acid? I'm not even clear on that. No, it's carbon monoxide. No, because it's got the 2 hydrogens on there.